So let's start the fifth problem. All right, so we have a slender 6 kilogram bar that is horizontal and at rest, right? And the spring is unstretched. We need to determine the stiffness K of the spring such that the motion at the bar is momentarily stopped when it has rotated 90 degrees clockwise after being released, right? So first thing, we'll just redraw the before and after, right? So as you start, your object, of course, is the bar. We have this bar here, AB. You have a spring on it, right? And then you want to, so that's it's at time 1. And then at time 2, it's going to be like this, right? A here, B here. And then you'll have your spring all the way here. Right, and I'll mention this because I'll need it after, right? So 2 meters here. This is 1.5 meters. This is 2 meters, and then this to this is 3.5 meters. All right, and then the next step is to set up our equation, right? Because we could use kinematics here, do the sum of forces, x, y, but you'll end up with like some nasty integral to do along the path, right? So the best thing to do is just use energy. So there's like 2 main energy formulas, I would say. They're basically the same. I think maybe in class you saw this one here. That's like T1 plus V1 equals T2 plus V2, with where T basically is the like kinematic, everything that has to do with the movement, and V is all the energy that has to do with potential, so gravitational and the spring, right? I prefer this equation here just because it's a little bit more obvious what we're doing. Finish writing it up and explain it a little bit more. All right, and basically K for kinematic, right? So this is my kinematic energy at state 1, gravitational potential energy, my potential energy coming from the spring, any work that I do on the system, and same thing here on the other side, except this it could be external or thermal, right? Which is basically the friction term, because the friction will always appear like on this side because it will always consume energy, right? So it will, if we had to put it, consider it, this would be how it goes, right? But for our case here, basically we would want to make it easy on us, right? So the first thing to do is place our reference point, which I'll choose to put like this here, right? So I don't have to take into account the potential energy at the first layer, at the first in the first thing, right? Therefore, I know we start at rest, so this is 0. I know that I have no potential energy, that's 0. The spring starts unstretched, it's 0. There is no work in my system. At the end, I have no more kinetic energy. I will have some potential energy. I will have some spring also. And there's no friction, right? So basically, we just need to find these terms now. So for UG2, it will just be the change of height, right, times mass times J. So the change of height is going to be, so let's read this here. So we got to be careful here because it's the change of height of the bar, right? But more precisely, the center of mass of the bar, right? So the center of mass starts here, ends up here, 1 meter away, right? So my change of height is going to be -1. All right, so I have -1 times the mass, which is given to be 6 kilograms. So 6 times 9.81, which is going to be equal to 58 negative 58.86. All right, joules, because this is energy, right? And then for the spring, so for the spring, it's going to be 1 over 2 k delta s squared, right? Delta s being just the change of length. And so I'm going to come back here, right? So the length at the beginning is 1.5. Right, so let's say S1 equals 1.5 meters. And then S2, I'm going to use Pythagoras here to find this length here, basically. And so S2 is going to be 3.5 squared plus 2 squared square root, right? Which should give us a value of square root of 65 over 2. All right, so delta S is going to be equal to square root of 65 over 2 minus 1.5 meters, which is what I'm going to put here, right? I'll have 1.2 k square root of 65 over 2 minus 1.5 squared, which gives me a final value of 3.20 k, right? And now I can use this equation here. So I know that 0 is going to be equal to minus 58.86 plus 3.20 k. So my k has to be 58.86, 3.2, which gives a final value of 18.4 Newton per meter. And that's how you solve this problem.